Okay, there you are. So first, I'm going to show you step by step how to implement the elliptic curve digital signature algorithm. Okay. So I've copied each of these steps from the description of it from last time, which I presented at the very end. So I'll talk about each one in some detail. And then after this step, I have actually carried out this step in code in Sage. Okay. So the first step, to set up the elliptic curve digital signature algorithm, you choose a prime number q, and here's how to choose a prime number q, and an elliptic curve e modulo q, and a point g of some prime order p. So I'll tell you in a minute how to do that. And you define a set theoretic map in any way at all from fq, the integers modulo q, to the non-zero integers modulo p. And then you choose a random secret number d in fp star, and you let q be d times g. So you do that calculation on the group. This means add g to itself d times. And then finally, your public key is the elliptic curve, the point of prime order p, the multiple d times g, which we're calling q, of that point, and the prime number p. And the private key, the information you keep secret, is d. Okay, so this is something that you want distributed widely. You put it on your website, you put it in directories, whatever. That's what the EGQP is. It's your public key. The private key you keep very secret. All right? Under lock and key. Somehow encrypted. Or something. Anyways, you don't want anyone to see that. All right, so now let's do this in practice in a particular example. First, here's a random prime. I guess that's not very random, because it's the next prime after 2 to the 128. Actually, it doesn't need to be random. It's just some prime number. So there you are. There's a prime number. Here, fq means the finite field of order q. Z mod qz is a field in addition to being a ring when q is prime. And so this thing, which I call gfq, or just fq, for short, gf, by the way, stands for Galois field. That's just standard, Galois field. Or Galois is, of course, the mathematician that died young and did a lot of stuff in algebra. But it's also the name of the company that somebody who was in our class last week just got recruited to and will no longer be here. This guy Rex was here last week, and then he went to interview at a company called Galois in Portland. They hired him, and now he gets to program full-time in Haskell for a living. So he's gone. Thanks to Galois. Okay, so that's what GF stands for, Galois field. And again, this is something you're very familiar with. It's just 0, 1, 2, all the way up through q minus 1 under arithmetic mod q. Okay? All right, and now let's make our elliptic curve. And I'm just going to make it be the elliptic curve y squared equals x cubed plus 3 times x plus 4. There are many possibilities for choosing. Basically, if you choose any random values in A and B, of A and B, it's highly likely they'll define an elliptic curve. And so you just choose some random values, and there you are. However, once this has happened and you start using this elliptic curve in cryptography, you might start wondering whether it was a good idea to choose it the way you did. Maybe you made your choice badly. And there's a lot of wonder about that. For example, in Bitcoin, as I'll show you later, I figured out, it was actually surprisingly hard to do, I figured out exactly what the elliptic curve is they use. In all of Bitcoin, they use exactly one elliptic curve. And you'll see it at the bottom of the notes for today. And there are extensive discussions that go on for pages and pages online in which people wonder, was this a good choice of an elliptic curve? Because it's actually a really special curve. And nobody knows for sure why that was chosen, because the person who chose it is anonymous. Or nobody knows who he is. Okay, so this particular elliptic curve, we can call the cardinality function after we make the curve. That's the thing I talked about before. It uses this algorithm that Scove invented, which involves computing the cardinality mod a bunch of small primes and then using the Chinese remainder theorem. So you ask for the cardinality and then you factor it. Notice in this case it turns out to be a product of a couple of very small primes and then a large prime. That's good. That means if we take a random point on this curve, it's probably going to have order closely related to this. We can just multiply it by something little to get something of this big order right here. If this were a product of a whole bunch of small primes and there was no big prime, would that set off any alarm bells for you? Well, yeah, that's true. But why would it be bad if the cardinality was just a product of small primes? Like, what would go wrong? Why would you be, if your employee said, I want to use this curve and its cardinality is 2 times 3 times 5 times 5 times 5 times 7, and it was all small primes, why would you be like, bad idea?
Isn't it almost same as finding discrete
Yeah. So it's basically the same problem. You can solve the discrete log problem really easily if your group has order that's a product of a whole bunch of small primes. But also in this case, you have to choose a point on the curve of prime order. And the order of a point divides the order of the group. The order of an element of a group divides the order of the group. And so if this number, the cardinality of E, is a product of small primes, then any prime divisor of it is small. And therefore, G up there, that point G right here is going to have small order. And probably whatever this cryptosystem is, it's going to rely on the discrete log problem in the group generated by G. Well, it does. And if G has very small order, then it's extremely easy to crack the discrete log problem. You can solve it. So you want G to have large order. You want this P to be large. And so it's good that this just is a couple of small primes and one big one. Ideally, you'd want it to be just prime. For example, the Bitcoin curve again, which we'll see later, its cardinality is a prime. There's no small primes at all. Just one big prime. So, yes?
How do we find the cardinality again?
Just E dot cardinality. That's the function in Sage. Do you mean what's the underlying algorithm?
Yes.
It's extremely complicated, and I haven't explained it. It's a very clever and surprising algorithm invented by René Scoof, and the algorithm itself is basically involves some ideas from modular forms, modular functions. I mean, it's actually related to your project, so you're the only person here that probably understands what I mean by that. But what it amounts to is computing with the 7 torsion, 11 torsion, 13 torsion points on this elliptic curve for a whole bunch of different numbers, 11, 13, 17, 19, and so on. And you do a calculation with those torsion points, and it gives you information related to the characteristic polynomial of Frobenius. And from that, you get information about this cardinality mod multiple primes. And then you use the Chinese remainder theorem to combine that information together to get the cardinality. It's a very surprising indirect route to this cardinality, but it works. Okay? I don't know if there's any fairly elementary explanations of this. I've never seen anything that wasn't just aimed at experts, unfortunately. And I've never seen anyone write a project on how this algorithm works. Okay, so I wanted a point on the curve, P. Well, actually, I want a point G of prime order. And so I'm going to call E dot random point, and that'll just give me some point on the curve. The way that works, by the way, is it just tries a random value of x and then checks to see if, when you try to solve for y, there's a solution, mod q. Either there is or there isn't, and the probability is like 50-50, whether or not there'll be a solution. So it just tries a random x, and then it tries another random x, and then another random x, until it finds one that works. At least that's the way it was when I implemented it. I remember somebody complaining that it wasn't truly random, like the distribution wouldn't be perfectly uniform, so then they slightly tweaked the code or something. But I don't remember. Well, one thing in Sage, by the way, is you can do this. Let's see. I don't know whether I have to reevaluate this. If you have a function in Sage, you can type 2 question marks after it and hit enter, and that will output the entire source code. So here's the source code for the random point function. It's in this file right here, which you could open if you wanted. And then here's the documentation And there's some issues with it, which were fixed in a track ticket. And then this is the actual source code. So that's the complete source code for the random point function. So what it actually does is, let's see, apparently it does something special in the case of 2, 3, and 4. And does something else to deal with the fact that it wasn't random the way it was down here. But then finally, after these special cases, it then just chooses a random x coordinate and tries to find a corresponding y coordinate, and if it finds one, then it returns that. Okay, so that's the actual source code in Python for the random point function. When I implemented this the first time, it was just this, basically. And of course, people complained left and right because they tried it for, very small primes. For elliptic curves mod, a very small prime, and it gave, maybe they drew a histogram, and they're like, that's not a uniform random distribution, so they complained. Yes?
So is it like this formula is like truly random?
Well, it uses the random number generator that uses a system-wide, or not system-wide, but when you start up Sage, it initializes a pseudo-random number generator using information from the system, and it uses that to generate the random numbers. So it's not truly random, it's pseudo-random, which is the case of everything in software, pretty much. Unless you have like some special device attached to your computer or some special hardware that provides more randomness than you get from the time of day and other events happening. I mean, some of you noticed that you couldn't get sufficient randomness in order to generate a GPG key when you were trying to generate your GPG keys. And what happens is the system just kind of looks at random stuff that's happening, like how quickly you're typing, which is more random than other things. It tries to make random numbers, but excuse me. But sometimes it can't. Okay, so that's the source code for random element, etc. Okay, so I found this point, and because I wanted it to be the same when I did it again, and I didn't want to explicitly set the random seed, which is another function, set random seed, which allows you to make the random numbers always the same. I just said p equals e of, and I put the point back in. I computed the order of the point, and it's not prime. It's 2 times a prime. But if you take an element of a group of order twice a prime and multiply that element by 2, namely add it to itself, 2 times p, then you'll get something of order the prime. So that's what I did. And I defined that to be g. G is twice this point. So now I have a point g of prime order, and here I'll evaluate this. So I didn't actually print out the point here. So there's the point of prime order, and there's the prime order of the point. Namely this number right here. All right, so we have almost everything we need to do ECDSA. One other thing we need is our secret key, and we also need this funny map phi. Okay, so we have our point G, and we have FP. So I'm defining phi as follows. What it does is it takes a number mod q, the lift method that takes the number mod q, which is it's like a number between 0 and q minus 1. It's not an actual integer, it's a number mod q, so it remembers that it's modulo q, and it lifts it to an integer. It chooses that integer in the interval between 0 and q minus 1 that reduces to it. So it's like that representative of the equivalence class. So it chooses that lift, and then I just reduce that lift mod p. So that's a map from fq to fp. It's not a group homomorphism. It's not algebraic in any way. It's just a set theoretic map from fq to fp. And then I had this funny condition. I don't want it to ever give 0. So if it happens to give 0, I just make it 1 instead. So that's the one funny thing. And then I return that value. So that's what this function does. Okay, so I can apply that to any element mod q, and it will give me back a number mod p. Okay, so that's what phi does. And I generated a random secret d, which, again, it would come out differently if I were to reevaluate that. So I'll just hard code it. Okay, so we now have our random secret d. D is a number modulo p, and it's that number right there. Okay, that's the secret key. The public key is everything else. And let's see, let's compute Q, which is D times G. Okay, and now we have our public key. Here, I'll print the public key out. Okay, there it is. So the public key is this point Q, it's the prime number P, it's the elliptic curve, and it's the point G. It's all that data. And now we can easily sign stuff. Any questions? Okay, let's sign something using this public key. Okay, I decided that, remember I'm not saying much about hash functions and so on, but I thought I might as well just show you how to do it in Python. It's really easy. There's a library that just comes standard with Python, any copy of Python anywhere, called hashlib. Hashlib, you can just import it, you can go to the Python website and look at the documentation, whatever. It provides a whole bunch of different hash functions like SHA-1, which is used a lot in Git, by the way, and SHA-512, etc. So, by the way, if I import this and then do hashlib.tab, you'll see the various hash functions. So there's MD5, SHA-1, SHA-224, SHA-256, SHA-384, and SHA-512. Alright, we give up. So, okay. So there you are. You can take any text at all. It could be hundreds of pages of text. And then you can apply your hash function that you choose to that text. And then you call .hexdigest on it, and it'll give you back a hexadecimal string, which is annoyingly not a number modulo p. We want a number modulo p. So if you take that hexadecimal string and then use Python's built-in hash function, Python itself has a hash function that just gives you back a 64-bit integer. So let's evaluate this, and then call hash. That just gives you back a 64-bit integer. So that's kind of stupid. Since p is a lot bigger than that, I really should have, done something a little more clever, but that's what I'm going to do. So I take that, and then I reduce it mod p, and now I have a number modulo p. Okay, and there it is. So you could take any message at all and map it to give you a number modulo p, the hash of the message. And then this is the thing that you sign. And the idea of hash functions, by the way, is it's supposed to be, so the hash function takes the set of all finite strings, a string is just a finite list of letters, and it maps it to the list of all hexadecimal strings that are exactly this long. So one of those sets is infinite, and one of those sets is finite, right? The set of all strings is an infinite set, and the set of all whatever many digit hexadecimal strings given here of this length, that's a finite set. And so this function can't be a bijection. It's very much, infinitely many different things mapped to every single hash. However, the idea of cryptographic hash functions is you somehow make them in some clever way such that it's computationally difficult to find two different messages that hash to the same thing. Such a thing would be called a hash collision. So you don't really care too much if the hash takes a long time to compute. Like, you don't want it to be as fast as possible. That's not the goal here. The goal is that it's really hard to make another message that hashes to the same thing. Think if you could make another message, say, of your choosing, slightly modified that hashes to the same thing, then you could just take your message and append my signature of this hash and fool people, right? Like, what if this message was, I officially give you $1 bazillion, or actually, I officially give you $20, and you can somehow modify the message to say, I officially give you $100, and then you have some little funny character hidden off in there, and it has exactly the same hash. Then it would look like I've signed that message, but I haven't. I'd really signed this message. So you want it to be very hard to come up with different messages that hash to the same thing. That said, people have deployed famously various hash functions. Not this one, I think. And then by lots of hard thought, they've in some cases come up with ways of finding collisions via very hard calculations. And when that happens, then people get all excited and they worry about switching to a more secure hash function. So I think SHA-512 is a very good one, but it takes a while to compute. This SHA-1 should be pretty fast. Let's try it out. what did I do wrong? Time out. Oops, time it. Okay, so that's pretty fast. It's like a microsecond to compute. All right, so that's an example of a hash function. This hash function, on the other hand, the one that's in Python, it takes most any object in Python and gives you back a 64-bit int. This one is meant to have various properties. It's used a lot in internal data structures, like in the dictionaries. It's used for the set data type. Basically, it's used to make certain data structures more efficient. And if you ever take computer science classes with the topic data structures, you'll learn an enormous amount about how having a fast-to-compute hash, which gives you lots of different values for different inputs, can be extremely useful for data structures. Probably hash functions, the idea of hash functions, what you can do with them, is maybe one of the most central ideas in data structures. But this one's designed to just be very fast to compute. Nobody cares if you find collisions. That's not a big deal. What did I do wrong this time? Timeout. I'm like typing with an accent. Timeout. Okay, time it. And see, that's in the order of nanoseconds. So this one's just supposed to be very, very quick to compute. It's not even, it's like a tenth of a millisecond. Whereas this is 1,400 milliseconds. So this is like 14,000 times slower. Okay? So you can see that the optimization is very different. So anyways, this one ends up giving me a number which I can reduce mod p. And there we are. Okay, so now I have my z. And that z is the thing I'm going to digitally sign. And now we're going to run the algorithm. So pay attention. So remember, in the algorithm there were two steps. The way you sign a message is you choose a random number k, and you take and compute k times g. That is, you add g to itself k times. And then you do something, and this is kind of like doing half of Diffie-Hellman, or the other half maybe, I don't know. It's sort of like Diffie-Hellman, but different. So you then do something with k times g. Right here, you compute these things. And this is really easy to just type in. It looks weird. It's very unnatural looking, and it's somehow combining FP, I mean, it's combining different things in this picture. So in any case, let's do it. So we'll choose our random element. I'll just do this one differently. Okay. So now everything's going to be a little different than what I had below, but that's okay. So k is this random number right there. K times g is this thing. Pretty fast to compute. And then computing the final signature, that's the pair r comma s. That's the signature. And it's really, really easy to compute. I mean, here's all the code to compute it. It's one line. I mean, it's the same. It's like easier to compute. It's exactly the same as what I wrote up there. It's just the same thing. Okay, so that's how you sign a message. And the signature is, it's right there. It's the pair of these two numbers mod p. So I take my message that I had at the top, and then I hashed it enough to get a number mod p, and then I did this arithmetic on the elliptic curve, and I got a pair r comma s, and that's the signature. And that's what I might put at the bottom of my email message or something. And that should prove to you or make you convinced with high probability that I was the one that signed that message. The message might be, for example, a piece of software that is supposed to get installed on your iPhone or on your PlayStation 3. And when the hardware starts to run the program, it'll check that the signature actually matches. It'll hash the program and then check the signature, and if it doesn't match, it'll say, sorry, I'm not going to run this program. And in order to do that, to check that the signature works, which is what we're about to do in a second, notice that D, the secret key, is not needed. So you don't have to somehow put, like, on the motherboard of your PlayStation 3 or on your iPhone in some hidden place. You don't even have to put the private key, which is very important, because if you put the private key there, then people might be able to hack through it. Okay, so here is how you verify that the signature that we just computed is actually valid. So we're going to do two things. First, I'm just going to tell you the formula. You should not believe at all that this is a reasonable thing to do, but I'll prove to you, it's a little proposition, one line to prove it, that it is a reasonable thing to check. Okay, we'll do that right down there. But first, let's just do it and we'll see that it works out. So what you do is I'm not claiming this is reasonable, but it at least should be meaningful, okay? Because Z was the hash of our message, so it's a number mod P. S and R were the numbers in our signature. The signature is the pair S comma R. Or maybe it was R comma S. Yeah, it was R comma S. So these are numbers mod P, so it makes perfect sense to divide them. You can divide non-zero numbers mod P. G is a point of order P, and Q is also a point of order dividing P. So it makes sense to multiply it by something that's a number mod P. Because if you add G to itself lots of different times, if you change the thing if you multiply G by something, it doesn't, all that matters is what that something is modulo P. Okay? And so this is meaningful, at least. And when you do it, you get a point, because you're taking some multiple of this point plus some multiple of that point. You sum them together, you get a point on E. Okay? Now, if you take that point, and here's us actually doing this for the signature. If you take that point, and then what you do is you apply the function phi to the x coordinate of the point, and if that gives you r, you declare the signature valid. If it doesn't give you r, you say it isn't. Remember, this is just like with the RSA thing. You do some funny thing, namely, with RSA, you take the signature and you encrypt it using the public key, and if it gives you back the number, then if it gives you back the hash, then you're like, okay, that's right. If it doesn't give you back the hash, then it isn't. So this is the thing you do. And let's just do it, and then I'll prove to you that this is a reasonable thing to check. Okay, look, it worked. Woohoo! So I took C, that was Z divided by S times G, plus R divided by S times Q. I got this point on the curve, and then I applied phi to the x coordinate of the point. Remember, our points are represented as a triple, something, 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 and, well, you can see the point. It's something, something, something. If you do square brackets 0 in Python, that gives you back the 0th entry of the tuple. It's kind of weird, but that's the way it works. And if we apply phi to it, we get R. See, this is R up here, and that matches the R down there. Okay, so we've now done elliptic curve DSA, every single step of it. We've made our public key, we made a private key, we made up a message, we hashed the message, we signed the message, and then we verified the signature. Are any steps unclear? Just for practice, let's just do another one. Okay? Oh, I promised to prove that the calculation above was sensible. So before we do another one, let's prove this. So, proposition. If R and S is a valid signature, then we'll conclude that it's a valid signature via the process that we just did. Okay, so that's the proposition. And now here's the proof. So assuming it's valid, then S is by definition Z plus RD over K. Let's just quickly look back. Remember when it was just how we defined S. If you look up here, here's the formula for S. S is by definition Z plus RD divided by K. Okay? Just doing arithmetic mod P. Right? But now if you just flip it over, you can solve for K. So all I did was the algebra to solve for K. If S is Z plus RD over K, then K is Z plus RD over S. Right? Basic algebra. Okay, now K times G. Remember, G is our base point. K is some random number. We don't actually, so when you're verifying the signature, you don't know K. All you know is R and S. And you know the public key. You don't actually know what K is. Nonetheless, you can abstractly imagine multiplying K by G. So you don't literally know the information to compute this. Remember, so as the verifier of the signature, you don't know that, but it's there. So K times G, no matter what, has to be equal to Z divided by Z divided by S plus RD over S. All I'm doing is using the distributive rule of algebra here and writing it out. Okay? And then the next step is just to notice that by definition, D times G is Q. That's part of the public key, the Q. So again, we don't know D as the verifier of the signature, but this is just abstract mathematics. And so you look at, so K times G, whatever it is equal to this, but that has to equal this. But that's exactly, this thing over here, Z over S times G plus R over S times Q, that's something that we computed above using all the information we had, and that's what we defined C to be. That was literally this. This is just the hash of our message and the pieces of the signature and the pieces of the public key. So this was exactly the information that everybody has. And that's what C is. So we now know that C is actually K times G. So when we're computing C, we're really just computing K times G. And then the other part of the signature R, remember how that was defined? R was defined to be phi of x of K times G. Okay, so when we verify the signature here, all we're doing is via a little bit of funny algebra, we're computing K times G. That's what C is. We literally just compute K times G, and then we check that it has the same phi of x coordinate. Okay? So it's reasonable that the signature is correct. That we're very so. I mean, this calculation checks that. This calculation checks something that should be true if the signature is valid. It does not prove that this is a crypto system that cannot be broken. It doesn't prove that this crypto system is impossible to break, assuming the discrete log problem is hard. All it does is give you a kind of consistency check that this isn't a completely ridiculous thing to do, and that if the signature were correct, then this will be true. So it's just a consistency check. All right, let's do another document and make a massive mistake. Okay, so here we are. I'll make another message. I will hash it and compute the signature, which should come out differently because I changed some random numbers above. So my new message has signature, these two numbers. And now let's verify the signature. Okay, let's see if it works. It does, yes, look. 60769, 60769. That worked. Okay. Question, what serious mistake did we just make in using the digital signature algorithm? It worked. The numbers matched up. But we also just shot ourselves in the foot big time. The information that I've just given you by doing this, if I take those two messages and I publish the signatures that I just computed, anybody can figure out my private key instantly. Look, scrolling down. I made two signatures, right? That means I have two hash values, Z and Z2. And I also have two signatures, SR and S2R2. Look what happens if I just take the difference and divide. Oh, that gives me the random K that we used above, which is supposed to be secret. And moreover, if you take that and put in this little formula, which everybody knows everything in now, we all know K now because we just did that arithmetic. And we know S, Z, and R because they came in the signature. Boom, you get this number. But that was D, as you can see here. Just got the private key. Crazy, isn't it? So the mistake right here, our mistake was that we didn't generate a new random K. So every single time you sign a message, you have to generate a different new random value K and use K times G in the signature. If you don't do that, then the second you mess up and don't do that, or you somehow generate your random numbers not sufficiently random, then somebody can crack the crypto system just by looking at multiple signed messages. If you know the message and its signature, and you know two of them, then you're dead in the water. Example, Sony PlayStation 3. So this is the first slide of a talk by Overflow, which is about PlayStation 3's many failures in implementing crypto. And here's one of his slides, which explains how their random number K is chosen. They have a function getRandomNumber, and then this is from an XKCD comic. It's kind of a joke because you could, roll a dice once while you're writing the code, and 4 comes up. So you've chosen by a fair random dice the random number. But then you always use that same random number. You hard-code it in hardware. That would be very bad, right? Because then you just do a little arithmetic, and boom, you can recover from 2 signed documents the secret key. So, Actually, let me show you this talk a little bit. So it's extremely long, but get to the good stuff. So he has this little table which explains all the things that he wants to hack in the various systems. And okay, here's where we are right now, ECDSA. Let's keep going. So he's talking about how he hacked, or he and his group have hacked through various levels of security for PlayStation. I guess they wanted to run Linux on it, that sort of thing. So at this point, they want to get to the top, or they want to get far enough up that they can do whatever they want. So now here's what we're doing today, ECDSA. What is this? And so in his talk at this hacker conference, he explains exactly what I just explained to you. Tells you how the public key works, how the signature works, etc. And there it is. And then he talks about how like a good implementation should work where you use the dev random device to get some random data, etc. And then here's the Sony ECDSA code, which is less random. And that's how he describes their public key crypto. Because their failure here, all he did was take 2 signed games, and then he was able to figure out what their private key is. Even though the private key was not in the PlayStation. Like the actual device didn't have the private key in it, but the information needed to figure out the private key was there because their random numbers weren't random enough. This can confuse some people, so let's see.
Do the same thing with the Xbox then? Is that what the sign's saying?
I'm not sure.
No, they didn't fail. They didn't fail.
I guess I mean, they each have similar architectures, so I don't know what actually ended up happening. I don't know what public key cryptos in Xbox or anything else. And then somebody else is making some comments.
The checkboxes are for like what they have, and then
Yeah.
the epic fail is just for the PS3.
Right. Yeah, this talk's focused on PS3. Okay, here's something, unfortunately it's kind of small, but I guess I can see.
Eventually,
Use.
Sure.
So this is a message from like, I don't know, a few months ago, or last year actually, 2013, just on some random forum. Anyone still working on the ECDSA code? Blah, blah, blah. And he wants to like take apart the PS3 motherboard very carefully and disassemble the components and try to figure out what the private key is. And there's only one answer, which is the private keys are not in the PlayStation 3. And 4 exclamation points. They're in Sony's office. So Sony eventually fixed the problem and randomly generates their keys now. And so it doesn't matter. The key thing is, or the key, sorry, that was a pun. The key thing is that it's important to understand that if you do the crypto right, or even wrong, the key just isn't there. It's just that the information needed to deduce the key is there. Okay, so that's what happened with PlayStation. Next, Bitcoin. So I want to point out that this problem of random number generation with choosing the K in your implementation of ECDSA, so in Sony, they made a massive mistake. They just chose a constant value of K across the board. However, in Bitcoin, there was a major mistake in how the function, secure random is implemented in the Android operating system. Like from the get-go, it's like messed up for years. And there were a whole bunch of different Bitcoin programs that were implemented for Android smartphones, like this one. And they screwed up. They all relied on the random number generation in the Android operating system. And so this is a web page from August 2013, not that long ago. And it talks about how a recent component of Android responsible for generating secure random numbers contains a critical weakness, which is a real doozy. And basically every Bitcoin program in Android, because Bitcoin's cryptography system involves generating random numbers, is potentially at risk. And in fact, this was exploited, and very large amounts of Bitcoin were stolen from people in practice because of this mistake just a couple of months ago. If you look into what they actually did, here's a little description of the bug in Android. basically they just made a little programming error in some of the code so that when they're initializing some random number generator, they just like a bug in the, so here's the key thing, a bug in the code caused a pointer in the buffer to not be updated, which causes other code to overwrite portions of the seed, and the result is that there is only 64 bits of entropy in the buffer. So your random numbers, instead of being big, like they're claimed to be, really are just numbers up to 2 to the 60, well, somehow they only have 64 bits of entropy, whatever that means exactly. But the net upshot is that though the keys are randomly generated in these Bitcoin wallets, they're not random enough. And people can just watch the lack of randomness, look at a bunch of transactions, and then steal people's Bitcoin. And it has actually happened. Of course, Android got patched, but there's lots of old Android phones out there that aren't patched, so who knows. Finally, I'm going to tell you the elliptic curve used in Bitcoin in my remaining 5 minutes. Okay, so the elliptic curve is called SecP256K1. So everything I showed you above, those are kind of made up small examples. This is the actual elliptic curve. So it's the actual Q, the actual P, no like funny made up stuff. I'm giving you the actual details, okay? Of the public and, well, not private. Oh, I guess everybody generates their own private key by computing a random D, right? But everybody who uses Bitcoin, they're all using the same elliptic curve, the same point on that elliptic curve, everything. The only thing that's different is they generate a different random D to sign their transactions. So Q, the prime that you work modulo, is this prime right here. 2 to the power of 256 minus 2 to the 32, 2 to the 9, 2 to the 8, to the 7, to 6, 2, 4, 1. So it's that prime, which I can show it to you. And it is prime. It's that number right there. So all these Bitcoin things are working modulo that prime. And here's the elliptic curve. It's just y squared equals x cubed plus 7, which looks suspiciously simple. And a lot of people are paranoid over the suspiciously simple looking nature of this elliptic curve. But that is the one that's used in Bitcoin. It's called, the K right here in the name is K for Koblitz, where Neil Koblitz, here's his website, who I've mentioned before. He's a professor here, and here he is hiking in Peru. He studied elliptic curves. Well, he introduced these elliptic curves, and he also studied special properties of the curves that make it easier to compute things like k times g. And this curve is special, and it has extra structure that makes it so that you can compute k times g more quickly. And there's pages and pages of discussion online in the Bitcoin developer forums about the choice of this curve. And some people tried a random curve and made the arithmetic on the elliptic curve as fast as they could. Then they tried using this one to compare and use Neil's trick, and they found that they could get things to be about 30% faster. So that's one of the reasons that this special looking curve is chosen. On the other hand, it should make you very nervous because maybe there's a special technique for solving the discrete log problem on a curve with this surprisingly special looking form. That should make you nervous. I don't know. I mean, if there are people that are decades ahead in secret working on the elliptic curve discrete log problem, then they might know how to deal with this curve. And then they could steal all the Bitcoin they want. Okay, here's the cardinality of the curve, which obviously the calculation is very fast. See, 0.09 seconds, so super fast. To compute that, that's a prime number. And any random point on the curve will give you something of that order, because that's the order of the group. But the point they actually use, so you can find online some representation in hexadecimal like this, but if you unwind things, it's this curve, it's this point right here. So this is the base point G that's used in the Bitcoin elliptic curve digital signature algorithm. And I just worked back and computed the string representation of the y coordinate in base 16, and it does match up with that one up there, I claim. 7.9 doesn't look like it. What the hell? Maybe I reevaluated it, but
I think it's in hexa.
what?
Is it in hexadecimal?
Yeah.
And you have something.
Well, this isn't hexadecimal. I've done this before. Let's see. This is wrong. Maybe I just need to reevaluate the blocks of code. because I could have reevaluated the wrong part after doing something way above. Okay. There could also be an issue with the order. What the heck? 7, 9. They don't look the same. 4, 8, 3. Well, I'm not sure why this doesn't. Not sure what the issue is. These should be the same, but they're not. Oh well. I'll check this later, but I mean, it's basically this. Okay, so that explicitly is should be the Bitcoin elliptic curve and the corresponding point. Okay, so now you've seen the elliptic curve digital signature algorithm. Any questions? Do you trust Bitcoin more or less?
I don't know why.
Why what?
Why not use dollars?
That is a whole different question. I think you have to ask drug dealers and assassins.